morning, good afternoon, good evening. Welcome to the last chapter of Biology 1. Yay! The last couple chapters we've been talking about the origin of the Earth. We've been talking about uh, evolution, natural selection, how animals got to be here, how the different kinds of plants and other living things that we see got to be here. Now what we're going to talk about today is how the Earth got to be here, and then we're going to talk about what's called macroevolution. Macroevolution as in the evolution of all of the major living things on the planet. The first thing that we need to understand is that our star is likely a second generation star. And what that means is there was another star and possibly another solar system here before our star was. That other star was huge, and that other star lived its life probably about 8 to 10 billion years, something like that, and then exploded. That's how stars die. Stars don't just go out like a light bulb. Stars go out like a firecracker. When a star burns out, it explodes. And the explosion of that star, the leftover mass of that star, is what created our entire solar system. Our sun, all of the planets, all of that was originally mass within a single gigantic star. So as I said, our sun is likely a second generation star. Our sun is probably about 5-ish billion years old. The planet, the Earth, is about 4.5 billion years old. It took probably about 500 million years for the Earth to cool off enough for any kind of life to occur on it. There was heat from nuclear decay. There was heat from all of the impacts. It was heat because it was a giant floating ball of lava. After about 500 million years, give or take, the Earth cooled enough that there could be life on it, except that there wasn't any life on it yet because life had not shown up yet. As I said, it took about 500 million-ish years for the Earth to cool. The first Earth's atmosphere, the early Earth's atmosphere, was probably water vapor and compounds from volcanic eruptions like carbon dioxide, like methane, like ammonia, like hydrogen sulfide. I do want you to note, look at that list, what's not in there. Oxygen. There's no oxygen in that list. There was no oxygen. There probably was no oxygen in the early Earth's atmosphere, which means any kind of living things that were going to show up, any kind of living things would have to do so in the absence of oxygen. And we've talked about this quite a while ago. There are some organisms, there are some bacteria that can live in the absence of oxygen, and the early Earth's inhabitants, the first things that show up, had to do so in the absence of oxygen. With these mostly hazardous compounds, there was also a considerable amount of storm activity. Lightning, volcanic activity, ultraviolet radiation, all of these things were massive inputs of energy into these volatile clouds of all of these volatile gases. And if we mix these gases together, we mix together an energy source, what we can end up with is we can end up with some simple organic compounds. The oldest fossils that we have are in the form of what are called stromatolites. Stromatolites are about 3.5 billion years old. We've talked about this concept before. I want to talk about it one more time. When I say 3.5 billion years, what does 0.5 billion mean? 0.5 billion means 500 million. So the 0.5 in 3.5 billion years is 3,500,000,000 years old. 500 million. Never in a million years. 500 million. And that's just the 0.5. Stromatolites are 3.5 billion year old fossils of bacterial mats. Ancient photosynthetic prokaryotes, ancient photosynthetic bacteria that we actually still find today. This is an artist's rendering of what the early Earth's atmosphere, what the early Earth probably looked like. What I want you to pay particular close attention to is these dots that we see along this shoreline. We can see water, we see a caustic pool here, we see this dotted shoreline, volcanoes in the distance spewing out ash and lava. These stepping stones that we see right here are called stromatolites. Do a Google search for stromatolite and have a look at what they look like. They look like basically a pedestal of rock. This is a slice through one of these stromatolites, and you can clearly see, if you can't see in my picture, you can clearly see it when you look at the presentation on your own. You can clearly see the layers after layers of bacterial mats that lived one on top of another for literally millions of years. We still find stromatolites today. That's what this is a slice of, one of these stromatolites. These stromatolites, by cross-sectioning them and then by doing what's called radiometric dating, we can figure out how old they are. A couple things before we go very far. If I were to ask you the question, what are the oldest living things on the planet? What were the first living things on the planet? What's your answer? Dinosaurs! No, the first living things on the planet were not dinosaurs. They were probably bacteria or related to bacteria. They were probably prokaryotes. How do we know how old these bacteria were? How do we know how old they were? Well, we do what's called radiometric dating. Radiometric dating, the version of radiometric dating you're probably most familiar with, is called carbon dating. The way carbon dating works, it's this right here, carbon dating. The way carbon dating works is when we talked at the beginning of the semester and we talked about chemistry, we said, look, there's the normal version of an atom, and then there are the versions of the atom that have different numbers of neutrons. And at that time, we said that heavy versions of atoms, heavy isotopes, tend to be radioactive. Radioactive means they spontaneously decay. They spontaneously decay at a known rate. The half-life for the heavy version of carbon, called carbon-14, is about 5,700 years. And that means that if I have a pound of carbon-14 and I lock it away in a vault and I leave for 5,700 years and come back and take it out of the vault, how much of that pound will I have left? Well, half-life, I'll have half of a pound. And if I put that half a pound back in the vault and leave for 5,700 years and come back and take it back out, how much will I have left? Well, I'll have a quarter of it left, half of what was there. You put it in for 5,700 more years and bring it out, you have an eighth. 5,700 more years, you have a 16th. Half of what you have decays at this very constant rate. Carbon-14 is good up until about 70-ish thousand years, which means if it's been dead for longer than 70,000 years, there's not enough carbon-14 left to detect. The way radiometric dating works is we know how much of this radioactive version makes up a normal block of any amount of carbon, or in this case potassium down here. But if I have a brick of carbon, I know how many of those are radioactive. What's the percentage of it that should be radioactive? You stop adding new carbon to your body the day you die. So at that point, and every day you're alive, you're adding new carbon. You're constantly replenishing that radioactive carbon that your body spontaneously loses. When you die, you stop adding new carbon. So that's all the carbon-14 you're going to have. So every year you're dead, every decade you're dead, every century you're dead, there is less of that carbon-14. So you take a sample of your dead thing, and you see how much carbon-14 there is in it. What's the percentage of it is carbon-14? And then you look at how much it's supposed to be. If the thing were alive today, there'd be this much. But when my sample, I just find this much of it. So then you do the math and figure out, well, how long has it been dead for that much of it to have decayed? For that much of the carbon-14 to be missing? Again, if you know the half-life, we can do the math and figure out how long something's been dead. The problem with carbon-14 is it only lasts for about 70-ish thousand years until there's too little to be found. Well, that's way too young, 70,000 years. That's way too young to date these stromatolite things. So what do we use in that case? Well, in that case, we use potassium-40. Potassium-40 has a much longer half-life than carbon-14 does. We look at how much potassium-40 there is in there, how much is supposed to be in there, and then we do the math. And this is where we come up with these dates, these really, really long dates.